Hey everybody, today we're going to go over the Reynolds transport theorem and just talk a little about how we can use it to derive a conservation equation. So essentially, what the Reynolds transport theorem looks like is let's get this, like this. So it's the time derivative of the control volume of some quantity plus the control surface of that quantity times the velocity dA. And note that this is the perpendicular velocity, so you could actually do the dot n here is equal to your total change or your net change in the system. In this case, we have two terms here. This is our accumulation term. So this says essentially that this is the amount of stuff that accumulates in our system over time, or in our control volume. So this is like the stuff that is not accounted for by the flux. So this is our flux term, and this is what passes through our differential area, which in turn is pretty much saying this is what crosses our system boundaries. So this is what crosses in or out of system boundaries. The accumulation is actually what is, if something disappears within the system, but it doesn't cross the system boundaries, that would be something that would fall into our d over dt term. So this is stuff that's created or destroyed within the control volume itself. So if we look at this, and now we're trying to see how this applies to like the mass conservation, for example. So if we plug in, so Q is equal to big Q over volume. So if we were to plug in mass for big Q, we would have density is equal to mass over volume, right? And then we can plug this in for that, and then we have ddt control volume of density plus integral of the control surface times the density times the velocity, dot product with the normal vector, dA is equal to m dot net. And this is our conservation equation for mass. And yeah, so if you go through and you were to substitute instead of Q is equal to big Q, if you were to put momentum in there instead of mass, or if you were to plug in energy instead of mass, you could then go through and also derive those same equations using this same basic Reynolds transport theorem as well.